Okay, let us start the section, the module on quantum algorithms. We'll look at some simple quantum algorithms, and then the next module will be the advanced ones, which I still don't understand yet as of recording this video. But let's talk about the properties required for quantum algorithms. So the three main properties we're going to use are superposition. We're going to use entanglement, and we are familiar with superposition and entanglement from prior lessons, prior modules. And additionally, we're now going to use interference, which we haven't seen yet, but we will explain how it works through an application in Grover's algorithm. Okay, so interference essentially just the idea of amplifying the answers that are correct with a greater probability magnitude, and de-amplifying, I don't know what the word is, the opposite, but reducing the probability amplitude of those answers which are incorrect through repeated iteration. Okay, so now let us think about, or let us look at the typical structure of the quantum algorithms. So typically what happens is there is some circuit. We have some inputs in the top and some inputs in the bottom, and this is Q0 through some Qn, and this is Qn plus 1. This is the canonical circuit design. What happens is it goes through some function uf, and don't worry about the function right now. Just know this is the typical design, and what comes out is some output that is reversible, which is the main reason this output is even introduced in the first place, because all of these functions and operations that are done here and these black box functions must be reversible. So whatever the output is here, it's typically going to be Qn plus 1 XOR f of Q0 through Qn. And then on the top here will be, I believe, Q0 through Qn. Okay, so basically whenever you get a result from this, you can take these two outputs and reconstruct the original state and pass it back through this black box function to get the original starting position, which is a requirement of all quantum algorithms. So you're going to see this second output, the second layer of output in this canonical circuit design. It's going to be confusing on why it's there. You're not going to really see a need, and then we'll talk about whether it's actually needed in some cases or whether we can just ignore it in practice. But as far as the theory, we're going to keep it in for the rest of the lecture. Okay. And let's look at the first problem we're going to solve, which is we have some black box function, and we're going to call this an oracle. And we want to figure out if this oracle is a constant or balanced function. So for a constant function, and this is Deustch's algorithm, by the way. For a constant function, it's going to return f of 0 equals f of 1. And I forgot to say as well that it takes something from 0, 1 to 0, 1. So it's a 1-bit input and it's a 1-bit output. And we want to figure out if this function is constant or balanced. If it's constant, that means it's always the same output no matter what the input is. And if it's balanced, then f of 0 is precisely not equal to f of 1. And since these are the two outcomes in the sample space, then exactly 50% of the time is it f of 0 and 50% of the time is it f of 1. So that's something to know. When we're talking about constant or balance here, it does not mean that f of 0 and f of 1 can occur with varying probabilities. It can't be like 40 and 60%. It has to be 50% each. Okay, so traditionally to solve something like this, and we'll think about a classical query in conjunction with a quantum query or as a comparison, just so you can really understand where the power comes from. How would you typically query a function like this? Well, you would first query a 0, and you're going to get f of 0 equals something. But you don't know what f of 1 is. And there's no way to figure out what f of 1 is depending on f of 0, right? Because if the function's constant, then it's equal, but if the function's balanced, then it's specifically not equal, but you don't know if the function's constant or balanced at this point. So you have to query one more time, and once you query the second time, then you'll precisely figure out if they're equal to each other or not. If they're not equal, the function's balanced. If they're equal, it's constant. So it requires two queries in the classical setting, which is very little, but the quantum setting does one query, and that's kind of the foundation for understanding how there's a quantum speed up, even though here it's effectively pretty much useless and how much faster it is. Okay, so let's think about the quantum setting. So the design of Deustch's algorithm is essentially you start with let's do Q0 and Q1. And what happens is it passes through the top input passes through a Hadamard gate. The bottom input passes through a Hadamard gate as well. And both are passed into this black box function, UF. And the bottom one we will ignore. Okay, so we're going to go over what the inputs are at each stage of the circuit to like really understand what's going on. But what's happening is starting with Q0 and Q1, you're putting it in equal superposition, which is why we apply the Hadamard gates. And by putting in equal superposition, we're effectively testing all the possible inputs at once with one single query. So the 0 and 1 query are both queried at the exact same time under this setup. And also there's actually an X gate here. An X gate is applied first, and then it's a Hadamard gate, which is why I was confused earlier. Okay. And how does this circuit look on the inside? That was a point of confusion for me on a lot of the other algorithms. Basically, it's just specific. It's just a hard-coded mapping of f of 0 equals 1 or f of 0 equals 0 and so on. So this is literally two inputs hard-coded to two outputs. And someone designed that, and you want to figure out whether it's constant or balanced. So we already talked about how to classically query it. Now we're going to talk about how to quantumly query it. So at this point, after they both pass through the Hadamard, we have Q0, which starts in the state. Both of these qubits start in state 0, by the way. We have Q0 is now the plus state, and Q1 is the minus state because it was a 1, and then Hadamard applied to the 1 is minus. And now both of these will go into this function UF. Okay, so now after they pass through UF, there are a couple things to note. So remember from our canonical circuit design, what this bottom circuit does is it computes this result right here. Okay, so one thing I forgot to do is to write this 2-qubit system in its equivalent state. So we can write this as Q0, Q1, and that is the plus minus vector, which is equal to 1/2 times ket 0, 0 minus ket 0, 1 plus ket 1, 0 minus ket 1, 1. And this is just an expansion of this. You could do the tensor product of the plus and minus states, and you'll usually get the same result. But given this result, now if we pass it into the oracle function, what happens is the second qubit is, and the reason we are writing it like this and not keeping it in terms of plus or minus is because this f function is evaluated on zeros and ones, not pluses and minuses. So for us to interpret it, we need to be able to write it into this form first in order to like trace the circuit, which is something I think I missed the first time around, and then I edited it out. But once we have this state now for this position, we can move on to past UF. Once we apply UF, what happens is this gets transformed into 1/2 times ket 0, and we're going to tensor each one of these qubits with each other. So we have ket 0 tensor with what happens to 0? It goes into here. So 0 is the second qubit, so 0 replaces this q of n plus 1, and then it gets XORed with f of something. So it's 0 XOR f of 0. And it's this 0 goes right here, and this 0 goes into this 0 and the f of 0. So whatever this and this are matching, basically, as part of the canonical circuit design. So this is the first entry now. One thing you'll know is that 0 XOR something is just equal to that something, because the 0 does not influence any result. So we can just write f of 0 instead. And then we're going to continue this for the rest of the vectors. So this should be minus, and we keep the first input, first ket vector. And then for the second one, for a 1, what happens is a 1 is put into q of n plus 1. 1 XOR f of 0. And it's f of 0 because it's the same value as right here. And then we close that ket, and then we add ket 1 times, and this 1 right here is this the 0 is going to be 0 XOR f of 1, but of course the 0 XOR doesn't matter, so we just keep f of 1 only. And then we're finally going to add subtract, because we have to keep the same sign as right here. We have minus 1 ket, and then we have 1 XOR f of 1. Okay, so this is the state after passing it through this stage right here, after passing through the oracle function. So now let's look at two cases. Let's first look at the case where the function is balanced. So I'm going to keep this here. Can I change colors of this? No, I can't. Okay. So if the function's balanced, then we have f of 0 equals f of 1. And if f of 0 equals f of 1, we can replace everywhere in this top portion. Wherever f of 0 equals 1, we can rewrite it. So let's do this. And we can erase wherever it's an f of 0, we can, or wherever it's an f of 1, we can write f of 0 instead. So let's do it right here and right here. Okay, and now we can combine like terms. So what do we have here? We have 1/2 times, and we can pull out a ket 0 here. Ket 0 times f of 0 minus 1 XOR, and so the ket vectors. F of 0 minus 1 XOR f of 0. And that's from these two terms. And then we're going to add, does this parenthesis close the 1/2? It doesn't, right? Okay. And then we're going to take out a 1. Ket 1 times ket f of 0 minus 1 XOR f of 0. You should see some resemblance to the left side terms now that we already pulled out. We can pull these two terms out as a separate factor. So we have 1/2 times ket 0 plus ket 1 times this portion right here, which is f of 0 minus 1 XOR f of 0. Okay, and finally we can pull out a 1 over square root of 2 from this coefficient into here. So we have 1 over square root of 2 times the plus state times this portion right here. So when you measure, and now actually first you apply Hadamard after the state. Once you apply Hadamard, then you're going to get 1 over square root of 2, and plus becomes a 0. When you apply Hadamard and you measure, you're going to get a 0 in the top qubit with certainty. And if you get a 0 in the top qubit, that means the functions are balanced. And not necessarily that we know that relationship, that for sure if it's a 0 it's balanced, because we could get a 0 in the other one too, but I'll prove in the other instance why you're going to get something other than a 0, and that's why we know if we get a 0 we can attribute it to the functions being balanced, or function being constant. Sorry, I said balanced, but I mean constant. F of 0 equals f of 1 is the constant case. Okay, now let's look at where they are not equal. Okay, so the first thing to note is if they are balanced, that f of 0 can be rewritten as 1 XOR f of 1. And 1 XOR f of 1, why can f of 0 be written as that? So let's think about this. So if f of 0 equals 1, then f of 1 equals 0, because they are balanced and they have opposite answers. If that's the case, then 1 is equal to 1 XOR 0. That's true. Okay, now let's look at the other instance. So if f of 0 equals 0, then f of 1 equals 1. This is also a balanced case. If that's the case, then it's 0 equals 1 XOR 1, which is also true. So we can rewrite f of 0 as 1 XOR f of 1 in this instance, because we know there are limited outcomes for f of 0 and f of 1. Also, similarly, we have f of 1 is equal to 1 XOR f of 0. So that is something we're going to use in simplifying our algebra. So same way as we had earlier, we take these results and we plug in whatever we just got. So we have 1/2 times ket 0, and this times f of 0 minus ket 0, and then we're going to replace 1 XOR f of 0 as f of 1 now. So we took this portion and replaced it like that. And then we have 1 f of 1 minus 1, and 1 XOR f of 1 is f of 0 from above. So we have this. Okay, so now we can pull out a ket 0. So we have 1/2, pull out a ket 0, and we have this times ket f of 0 minus ket f of 1. And we can do the same thing here. So we have 1. We pull out a ket f of 1 minus ket f of 0. And what do we have here? We have these two terms are opposite because there's a negative sign, so we can factor out this minus, make that a plus, or make that a plus, make this a minus, and then pull a negative out here. It's all the same distributively. And then we have now 0 minus 1, so we have 1/2, and we're actually going to skip the steps that we know are going to happen. So we're going to do 1 over square root of 2 times ket minus, and then that is times ket f of 0 minus ket f of 1. And I think that's right. Okay, now once you apply Hadamard on the top input, which is this qubit right here, we're going to get a 1. And that's how you know you're going to deterministically get now when you measure a 1 if the functions are balanced rather than constant. So we know from just this circuit design right here, if we measure the top qubit at the end of it, if we get a 1, the functions are balanced. If we get a 0, they're constant. Okay, so that should explain Deustch's algorithm. There is also one more algorithm called Deustch-Jozsa, which is Deustch's algorithm built on even more. So let's get rid of that stuff right there. Okay, so Deustch-Jozsa instead, what it does is it knows that f is either constant or balanced, and it's the same 50% distribution thing as earlier, but rather than take something from 0, 1 to 0, 1, it takes an n-bit input, 0, 1 to the n, and it reduces it to a 1-bit output. And if that specific sequence is the correct one, or sorry, not the correct one, if the function that processes these n-bit strings returns a 0 50% of the time and a 1 50% of the time, then we say the function's balanced. If it returns a 1 100% of the time, or a 0 100% of the time, and the other one 0%, then we say it's constant. And how many queries would we need classically to query something like this? So we would need to literally write out and test out 0 0 0 until 0 0 0, where this is n bits, and we would need to check if the function returned a 1 or a 0. So let's say it returns a 1, then we're going to check 0 0 0 0 0 1, and we get a 1 as well. So we just keep doing this until we have checked over 50%, and once we have checked 50%, then we know, since if it's more than 50% of one of these outputs, then the function has to be constant, since if it's balanced, it's exactly 50%. And the only way to classically query this is to do it n times, or not n times, is to do it 2 to the n over 2 plus 1 times, which is a ton. Whereas the Deustch-Jozsa algorithm, Deustch Jozsa algorithm, what it does is it queries all of this at once and gives you your output instantly. And that circuit, it's not essential to like memorize exactly how it works, because it's beyond the scope of our course to be able to prove it. But what it does is it takes an n-bit input, which is all zeros. It takes the output, which is a 1. And you can also just think of this as a 0 with xk applied instantly. It puts them in superposition. And it puts every single bit into superposition. So we write that as that. It's h applied in sequence n times. So that looks like h, 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 and so on. The tensor of all the h matrices n times. And then they pass through the canonical circuit, UF, and UF has some kind of logic wired in it, so that depending on the input, it'll tell you if the output's correct or not. That could be a hard-coded case for all of them, or it could be something like if the first 50% of the possible strings are 0, then it's going to do something like literally if the middle element in the n-bit string is a 1, then you know it's greater than 50%, and so on. But someone will manually wire this oracle to give that logic. So I think that's something the lectures fail to explain. How is the oracle designed, or where does it come from? Someone creates this oracle, and that oracle has all of the inputs mapped to some particular output for the function. It doesn't necessarily have to hard code every single case, but if it warrants it, then they might do that, or they might write some clever logic on how to do it. They might do something like if the string mod 2 is equal to 0, then it's a 0, others it's a 1, and that happens exactly 50% of the time for an n-bit string. So that's how you could design a balanced function, for example. Okay, and then after that, you will basically apply Hadamard again to every single qubit, and then you're going to measure. And if you get a 0 0 0 0 as your output, then that means the function is constant. That means f of 0 equals the exact same thing for all. No, f of 0 equals f of 1, and the function returns the same thing for all inputs. If you get anything other than all zeros when you measure, if you get a 1 right here, for example, then the function's balanced. And you can get like a 1 in all the instances, then the function's balanced. You have to get a 0 in all the entries to make sure it's constant. That's Deustch-Jozsa. That's all we have to know for it. So I'm going to move on. Okay. And well, we talked about the classical query for Deustch-Jozsa was like 2 to the n over 2 plus 1 queries, which is a ton. But realistically, you could do like 20 to 30 queries using a classical setup and get a very small error bound, which is probably acceptable given realistically quantum computing has its own errors in doing these algorithms and whatnot. Okay, so now let's look at the Bernstein-Vazirani problem. So we're going to first write their name, because why not? Bernstein-Vazirani. Okay. So we have some black box function, f, which takes an n-bit input and returns a 1-bit output. But as opposed to Deustch-Jozsa, which did the same thing, had the same domain and codomain, this being the domain, this being the codomain. As opposed to Deustch-Jozsa, Bernstein-Vazirani does not have it so that it is 50% or 100% and 0. It's not either a constant or balanced function we're trying to find. This time, Bernstein-Vazirani has some secret string s, which is n bits, and querying it will give you a 1 if you pass in s. It's going to give you a 0 for all other inputs. And sorry, no, that's not true. That is not true at all. That is Grover's algorithm. I'm confusing. It does have a secret string s, but what happens is the function does this operation s.x mod 2, and that result is going to be outputted by the function each time. So you can get zeros and ones a different number of times, but the goal is to try and find s given this function design. So one thing to do, or to first further explain, is what is s.x. So if s is some secret input 1011 and x is the input you're testing, then it would literally be like s0 times x0 XOR s1 times x1 XOR s2 times x2 and so on. And then that result is already going to be modulo 2. So the modulo 2 is what applies these XOR operators. And then the multiplication is why you multiply each index by each other. So it basically does the AND operation. So if this is like a 1 and a 0, then it's becomes 0. If it's a 1 and a 1, then it stays a 1. So it's like the AND truth table. So it does a bunch of ANDs, and then it XORs all those ANDs. And how does XOR work for multiple AND statements or multiple XORs in a sequence? Basically, if there is an odd number of 1s in the sequence, then it's going to return a 1. If there's an even number of 1s, it's going to return a 0. So like 1 XOR 1 is going to return a 0. And 1 XOR 1 XOR 1, well, 1 XOR 1 will be 0. XOR 1 will return a 1. So you can basically generalize it to like how many 1s or 0s are there. And that's why you also have the mod 2, which is literally the test for whether something's even or odd. So it just tells you whether there's an even number or odd number of AND statements that are true. Okay, so that is the problem statement. Let's design the circuit for this. So the circuit looks like, let's say for a 4-bit input, which we can use the same secret string here. We'll have x0, x1, x2, x3, and a temp variable. So to design the circuit, we're going to have it so we have a sequence of C-naughts that will constantly flip some temp variable, and the temp variable will store the result of this whole operation. So the C-naughts will look something like, since the first one is a 1, it will be something like if you pass in I think before I say that, I should also mention that, remember in this operation here, that if any one of S0 or X0 is a 0, then instantly that whole part evaluates to 0. So in this instance, where a 0 is in the second index, which belong to this entry, then we can instantly convert this to a 0, so we don't need to consider what the second index is in the n-bit input that someone passes in. So if I query a 1, 1, 1, 1, then this thing should just be ignored completely, since it's anyways not going to contribute to the output at all. So basically that's the idea behind CNOTs. For everything that is active here, it flips the temp variable and it will return the exact same number of variables, or exact same number result of this operation right here. So we'll trace that as well. So S0 times X0, that means we have a control right here on X0, and it flips the temp variable. We also have a control on X2, and it flips the temp variable. And we have a control on X3, and that flips the temp variable as well. Okay, so this is what the circuit would look like in the black box function. This is how you would design it. And if you queried a, let's say 0, 0, 0, 1, then what happens is it checks first for X0. If there's anything, it does not flip the temp variable. This does not flip the temp variable. This does not flip the temp variable, and this flips the temp variable because of the CNOT right here. So the temp variable would be 1. And that's exactly the, if you did the inner product of these two, you'll get just 1 XOR 1. You'll get like a bunch of zeros XORed with 1. And I realized I should have done a proper 0 here, since that looks like an XOR. And that's going to have just a 1 when it does mod 2 from this function right here. So you can see that it's basically creating the same math right here by doing this circuit design. So this is we know exactly this is how the function is going to be designed for this particular problem. Though when we're actually querying this function, this is completely invisible to us, so we don't see these CNOTs, we don't know their locations, but we do know that that's how it's set up on the inside. And that's going to prove really useful in solving this problem. So we know that is true. This is how the circuit has to be designed quantumly. Okay, so now there's something called the CNOT reversal trick. And what CNOT reversal does is it finds that for a circuit, you can actually have an equivalent reversed effect by applying Hadamard's prior to the opposite CNOT direction. And then Hadamard's after as well. So these two circuits are equivalent. You're going to get the exact same result, and you can verify that using matrix algebra if it's not convincing. But otherwise, you can just take that as a result and know that these two are equivalent. So essentially, if this Q0 is a target or Q0 is the control and Q1 is the target, then applying this sequence will flip it so that Q1 is the control and then Q0 is the target. This is what this gate on the right does. This circuit on the right does. Okay, so using this, if we now have our original CNOT sequence like this in the function, which is the oracle, if we apply Hadamard's on the n qubits on the outside and the temp qubit as well, and we apply Hadamard's afterwards, then it should be equivalent. It should be equivalent to swapping the CNOTs in every single one of these locations on the circuit. So we would get something like let's erase the temps right here. We would get something like this. So by doing this, now we are basically saying that if the temp variable is a 1, then I want you to light up all of these portions that have CNOTs attached to them, because now we've reversed the CNOT so that whatever was the control qubit is now a target qubit, and we have the control qubit fixed as 1 from our input. So it's going to light up all of those former control qubits as the new target qubits. And then once we get our output and we measure, it's exactly going to be equal to that sequence that we're looking for, S. So the way to do this as well is also to initialize temp as a 1 by doing a bit flip initially, before actually passing into the Oracle function. So this is the main idea behind the C0 reversal application. You use this equivalent quantum circuit and you change it so that since you know the Oracle function will be designed like this, even though you can't actually see where the C0s are, you know the structure has to be like that. So once you apply the C0 reversal, you're going to get a structure that basically highlights all of x0, x2, and x3, given the temp variable will be a 1 when you pass it in. And that is basically all of Bernstein-Vazirani. So by passing in this and passing in a set of n plus 1 qubits initialized at 0, and you pass it into this circuit above here, then you're going to get 0, 0, 0, 0, 1. And once you apply Hadamard on everything, you apply the Oracle function, you apply Hadamard again, and if you measure that result, you're going to get the secret string S 100% of the time with full guarantee. So that is Bernstein-Vazirani. So to query something like this, you just need one query. And what would it look like if you did a classical query? So in this Oracle function setup right here, to classically query all of these results, you would have to do n queries. You would have to query the first bit and then see how you would do something like 1 0 0 0 0, and you would see how that affects the input or affects the output. Then you'll do something like 0 1 0 0 0. You'll see how that affects the output. 0 0 1 0 0. You'll see how that affects the output. And you have to query n times for the n permutes of a single bit being in the set of qubits in the sequence. And the classical query takes n times, the quantum query takes only one time, but it requires n plus 1 qubits, the n qubits for the x0 through x3 plus the temp qubit. Okay, so that is Bernstein-Vazirani. Next is Grover's algorithm, which is this guy right here. And a word of caution about Grover's algorithm. In the lectures, and this is why I was so confused for so long, in the lectures, he promises it like you can look through an unstructured database, 1 to 72, blue, apple, and you can find any particular element you want, and you can find the index it's at. And the main question was, how in the world can the Oracle function know that? And the truth is, it doesn't. So this problem is not actually what you can solve given the steps we do in this lecture. Now, with additional modifications to the Oracle function and some additional pre-processing, you can set up a problem like this. But for the scope of our lectures, we do not need to know this database lookup. Just know it's possible, but we don't need to know how to actually do that in practice. And if you'll remember from our grade scope problem, the one where it asks us to do the rotation and inversion right here for the Grover circuit, we have to implement a Grover circuit and then find the secret string. That is a better example or application of Grover's algorithm than the database lookup. Even though the database lookup is possible, that's not in the scope of how we learn Grover's. So don't bother trying to confuse yourself on how you can do it, because they do not give you enough explanation on how to do that. No resource does out there right now, because it seriously requires so much pre-processing to be able to set up something like that. Okay, so now let's consider the problem of, rather than speeding up a database lookup, you can still think of it as a database, but instead it's going to be a database of a sequence of numbers. So it might be like that, and it does not have to be sorted, but the problem here is we have some secret string S, some key that we're looking for, and we want to find out what that key is using a Grover's query. And typically, to sort through a structure like this, classically, it would take n over 2 queries on average, because in a list of n elements where they're not necessarily sorted, you could get it on the first try, you can get it on the last try, you can get it on the middle try, and if you average it all out, it's n over 2 tries on average, so it's linear. linear query time. With Grover's algorithm, it takes square root of n times, which is a quadratic speed up, but it is this is on a unsorted database structure, which is phenomenal. Okay, so let's think about how we're going to do it. First, let's talk about what Grover's algorithm does, and we're going to pretend we understand how the Oracle function, or we're not going to worry about how the Oracle function is designed right now, but somehow, some way, the Oracle function can highlight what the correct lookup location is. So if we have some sequence of entries, and these are the indices of the database, and let's say at this index is where our correct element or our correct key we're looking for is, then somehow or some way the Oracle knows to amplify and invert around this, which is the whole process we do square root of n times. But don't confuse yourself with how is the Oracle designed. I will talk about that right after this. But what Grover's algorithm does is it essentially rotates and inverts around the mean, and it does this process square root of n times. And after it has done that, there is a very strong chance that you have the correct answer. So basically, if you try to randomly select an element and try think about the probability of getting the right key just by randomly searching the database like this, the probability is 1 over n. And to get the probability amplitude in the ket vectors, it's just 1 over square root of n, because you square that result to get the actual probability, right? So if you do 1 over square root of n squared, you get 1 over n as a probability. So right now, all of the elements are in equal superposition, and they have a 1 over square root of n probability amplitude. Grover's algorithm applies a rotation operation, and the rotation operation is a unitary matrix, UF, and the rotation operation has it so that it is minus 1 to the f of x on the diagonals and 0 elsewhere. Okay, so f of x is just telling you it's going to return a 1 if the secret string is correct, or the key is correct, and it's going to return a 0 if not. So if it's a 0, it stays a 1. If it's a 1, then it becomes a -1 at that entry. And essentially what that does is it will flip only that entry once you apply this matrix, and it's going to do nothing to the rest of the entries. So this matrix is inherently designed in the Oracle once you implement it for a specific key. So what I'm doing in the circuit design is I'm saying, okay, hey, I want to design an Oracle, and I am some other party. I'm not the guy who's trying to guess where the location is. I'm some other party, and I'm saying that, okay, the key that you're looking for is 01000100. If you have this key, you'll be able to decrypt our data or whatever, and for re-encrypt it as well. And this key will be structured such in a circuit design such that it models this unitary matrix. And even though we're not directly creating the matrix manually and putting in those locations, it has the equivalent effect of creating a matrix just like this. So basically, we are effectively creating this matrix without anyone knowing how to put the entries where they are, which is a really mind-boggling thing to think about. But if you think about it in the context of keys, and you'll see later in the circuit design that we use from the grade scope problem, it's going to make much more sense. Don't worry if you're still confused. But basically, this rotation operator is applied to this setting right here. And for any entry that matches the key, then that will be flipped over as so. And the next step is the diffusion operator or the inversion operator, and it inverts it around the mean. So once we have our probability amplitude for the correct entry flipped, the mean becomes ever slightly lower because now it factors in that negative value right here. So it's going to be something less than 1 over square root of n. And what happens is you then take the mean and you flip everything around the mean. So this little bit by which the non-key entry is above the mean gets flipped below the mean. So that is the the destructive interference. So if this is 1 over square root of n at this line right here, then now each of those entries is slightly below that, and the correct entry is now flipped around the mean. So from here to here means the actual entry will be up here somewhere. So now that is where the correct location probability amplitude looks like. And everything else is slightly below that mean. Then you do the same operation again. You invert it around the x equals 0 axis or y equals 0 axis if this rotation operator suggests that it should be done like that, if that's the specific key you're looking for at that index. And it will flip it so it's hugely negative, and then to flip it back up so it's hugely positive again. It just keeps doing that again and again about square root of n times, and that's just an empirical result they found, and that'll give you a correct probability of if you measure it, you're going to get that location specifically. It'll look like 0, 0, 0, 0, 1, 0 is going to be the measured result pretty much, which means that the 1 was at the 5th entry, and that's how you know where the key is. So it might look something like that, basically. That's how the problem would be. And I think the way to think about this with now the problem we did in Gradescope, let's look at that. So we have some circuit here, and I think I'll take a picture of this. Okay, so I'm gonna remove this for now, and we'll come back and explain it later. But what it does is it takes Grover's circuit, and we have to implement this. So remember, for Grover's circuit, actually I don't think I mentioned it, but to test all the inputs, we first apply Hadamard on the inputs, and then once we get a uniform superposition, then we pass it through this rotation invert sequence. Because we want to check the superposition of all possible inputs at once, which is why we apply Hadamard. So in this sequence, the correct sequence here when doing Q0, Q1, Q2, I believe is, actually I think it's Q2, Q1, Q0. Is 110, I'm pretty sure, but we will check that. Or if you did Q0, Q1, Q2, it's sorry, I think I meant to say 011 right here. 011, and then this would be 110. So either of these will work. Let's look at the first example first. But how can we figure out to 011? We can do that by looking at the superposition of all the possible entries. So this is the rotation phase, and this is the inversion phase. So something to note about the rotation phase, inversion phase, about the circuit design, this inversion operator is fixed. So no matter what the key is, or no matter how you design the circuit, this inversion operator will always stay the same across all circuits, across all queries for the secret key, no matter how you design the circuit. This rotation operator is how you change it and how you make it for a specific key that is accepted. So all the information about the key should be contained within this rotation operator above. Okay, so we're going to look at the rotation operator. We're going to apply Hadamard to the entries first. So we start with 3 qubits all initialized at 0, and we apply Hadamard. So we get the plus, plus, plus states. Then we can expand this as 1 over square root of 2 to the 3rd power, I believe. And it would look like the ket 0 plus ket 1 vectors tensored with everything else. Plus ket 1. Okay, so now that we have this form, we are going to expand out, and I'm going to write root A instead of that. we're going to do the tensor product of all of this, which is going to be quite messy, but it's basically going to give us all the basis states because we have 0, 0, 0, then 0, 0, 1, and so on, and it's going to give us all the basis vectors. So we have 0, 0, 0, and I can just do it anyway. So this one, this one, this one, then that one. So 0, 0, 1, and then this, this, so 0, 1, 0. And we're going to do 0, 1, 1 now. And now we're going to do 1, 0, and so you can see the general pattern. So it's going to be 1, 0, 0, plus 1, 0, 1, plus 1, 1, 0, plus 1, 1, 1. So that is the expansion, the tensor product expansion of right here. Then we're going to apply the x gate to q0, wherever q0 is. Whatever q0 is, we flip it. So q0 is the rightmost qubit in this instance. We get 1 over square root of 8, and we're going to get, and actually I don't feel like writing that again, so let's just write it right over wherever it is. So this is supposed to be a 0 and a 1, so we're going to do 1 and a 0, and this is supposed to be a 0 and a 1, so we're going to do 1 and 0, that's then 1 and 0 again. Sorry, let me make sure it's clear. And then we have a 1 and a 0 in the end as well. Okay. And now we apply Hadamard onto the first entry. So Hadamard onto the first entry, the second qubit, but like leftmost entry, will give us, and I'm going to just write it out because it might be faster, plus 0, 1, plus 0, 0, plus 1, 1, plus 1, 0, plus minus 0, 1, plus minus 0, 0, plus minus 1, 1, plus minus 1, 0. Okay, to continue this explanation, I do want to quickly note out one thing. So I stopped for a second because I noted I never went over this, but there is this identity that the x gate applied to the minus state becomes a negative minus state. So there's a relative phase with that. Let's explain why that happens. So in the x gate we have 0, 1, 1, 0, and we apply this by the minus state, which is 1 over square root of 2 minus 1 over square root of 2, and we get minus 1 over square root of 2 and 1 over square root of 2. And so we have a minus 1 over square root of 2 in the top entry, 1 over square root of 2 in the bottom entry. We can't have that since 0 cannot have a phase, so we pull out a minus and we get 1 over square root of 2, and then minus 1 over square root of 2 on the bottom. So this is equal to the minus negative vector. So there is a global phase in this, which is a lot of the source of the confusion, but something to note. So among these 8 basis states, what step have we last applied? We applied the Hadamard to Q2. Now we're going to move on to the controlled CNOT gate. The controlled CNOT gate essentially performs a bit flip. It performs the X gate on Q2 if Q0 and Q1 are 1. And where does that happen? That happens in this instance and this instance. So all the other instances will remain unchanged. In this instance, if you apply H to the positive, it doesn't do anything, and you can verify that with the if you perform a X onto the positive, it doesn't do anything. You can verify that with the matrix vector algebra. So like 0, 1, 1, 0 applied to 1, 1, and then 1 over square root of 2 is pulled out, will return the exact same result. So this will stay plus 1, 1, and then this entry will become a minus 1, 1. So now it has a relative phase induced. Okay. And once we have done that step, then we apply X onto Q0, and we apply H onto Q2. So X onto Q0 will do this. So we have plus 0 plus 0 0 plus 0 1 plus 1 0 plus 1 1 plus minus 0 0 plus minus 0 1, and then we have a negative now that we pulled out from right here, so it is minus 1 0 and plus minus 1 1. Okay, cool. I think this is not needed. Okay, so after that we apply h to the leftmost cubic, which is q2, and we get 1 over square root of 8 times, and we get a 0 0 0 plus a 0 0 1. So you can see it's kind of unraveling the results from earlier, but it now has performed a relative phase on the secret string that we're looking for. And it's going to do a 0 1 0 and 0 1 1 and a 1 0 0 and a 1 0 1 and a 1 1 0 and a 1 1 1. So these are all the basis states, which are identical to this step from earlier, but now there is a negative phase induced on the key we're looking for, which is 1 1 0, and that is how we find our key, by applying Hadamard to do uniform superposition on everything first. So what happens with Grover's algorithm is now this 1 1 0 is negative from this rotation operator, and it only applies to the secret string we're looking for. And then the inversion operation amplifies the probability, it inverts again, it amplifies the probability, and then after about square root of n queries, it has 1 1 0 having a disproportionately high probability amplitude when it measures, and all the other ones have very, very small probability amplitude. So 1 1 0 is the secret string that we were looking for, and we were able to query that quantumly. If we did it classically, let's say we tried to classically query this circuit right here, then we would have to try every single input, and it would take about O of n tries on average, but it would look something like we pass in a 0 0 0, and 0 0 0 will return out as 0 0 0 with no phase. So then we know it's not the correct choice. And then if we do something like 1 1 0, which is our correct answer, and ignore the 0 1 1 up here, I think I mixed it up. If we did 1 1 0, which is the correct selection, then if we applied it and passed it through UF, we would get a minus on the outside of it, and it would amplify this significantly. So classically, that's how you would query given this quantum circuit, but we are quantumly querying using Hadamard and this rotation and inversion operation. So that's Grover's algorithm. It requires one query of inputs, but it requires square root of n iterations. So that's why it has a complexity of square root of n, whereas classically you would just pass it into this rotation operator and get your result if it has a negative or not on the end of it, because you don't need to do this operation on the classical inputs to get your output, because the phase will tell you whether it's the correct string or not, correct key. So that is Grover's algorithm. I think that's all of the algorithms I want to say. To iterate over Grover's algorithm and why it was so confusing, this circuit is designed by someone, and they have some key they are trying to hide in the circuit, and the only way to, like, we can think of this as a password for some kind of, I don't know, a website or something like that. There's obviously a more complex relationship right here, but let's say it's a password to a website and you want to get in, and the only way to get it is by querying that specific key. So classically you would query about n over 2 tries, and using Grover's you would take square root of n iterations, and you'll find out that key, and then you can classically query the key you found quantumly into this, and then you'll be accepted into the website. So that's the example usage with a key and a string. as opposed to a database lookup, which was a very, very confusing example that they gave in the lectures that doesn't really work here. Okay, I think that should explain everything. I got some editing to do. I will see you later.